All right, hello everyone, and welcome to the AstroCheminar for the month of October in 2022. I'm glad to have you all here. Before we get started with our presentations today, I have a few announcements. If you are subscribed to our mailing list, then you heard about these things this morning in an email that was sent out by our Subdivision Secretary Dave Woon. So there are two conference announcements. There's a conference on dust, ice, and gas astrochemistry that was going to be held November 17th and 18th. That's an online conference, and in Dave's email there was a link to more information. We're going to get that link posted for you in the chat. There it is. And secondly, we have there's going to be a laboratory astrophysics workshop called ICE 2024 that's going to be held in Hawaii in February of 2024. And again, there's a link with information about the organizers and more details on that conference that was just posted in the chat and is in Dave's email. So if you did not receive Dave's email, then I would encourage you to please go to our ACS Astrochemistry Subdivision website, where you can sign up for the mailing list and get more information about our upcoming AstroCheminar events and other activities of the subdivision. But again, I'm glad to have you all here today. My name is Kyle Crabtree. I'm the chair of the Astrochemistry Subdivision, and I'm joined here today by our past chair, Heather Abbott-Lyon, and our chair-elect, Chris Bennett, who's currently occupying the ACS Physical Chemistry Subdivision, the Physical Chemistry Division account. We're grateful to the ACS Phys Division for letting us use this Zoom webinar platform. And we have two seminars for you today. And I'm going to first introduce our first speaker is Dr. Elettra Piacentino. Dr. Piacentino comes from Italy, where she received a bachelor's degree at the University of Pisa and then came over to the US to do a PhD at Northern Illinois University on the general subject of metal catalyzed formation of formic acid. And she's currently a postdoc at the Harvard-Smithsonian Center for Astrophysics, working with Professor Karin Oberg. So Dr. Piacentino, you can go ahead and start sharing your slides, and I will hand things over to you.
Sorry. Can you see it right? Well, thank you for the nice introduction and for inviting me here today. So what I want to tell you today about is what I learned so far about the chemistry of phosphorus on interstellar grain during cloud evolution. And we all know how important phosphorus is. We know that it takes part of all different branches of biology, is important for structural aspect of cellular walls, for example, is used as an energy currency, but also takes part on storage and transfer of biological information. So phosphorus is really important for life and on Earth. But when we move in space and we start to look at where phosphorus is and how abundant it is, we find something a little bit different. In a diffuse cloud scenario, we know how much phosphorus is there, and we know that is mostly present in its atomic form. But then as the cloud evolved, this phosphorus would take different shapes. And if we take, for example, planets and planetesimal, we find phosphorus that is mostly carried by phosphorus monoxide and is present with an abundance that we expect, with the abundance that we expect to see. And one of the most recent detection of phosphorus monoxide is on Comet 67. So we have the starting and the ending point of the story, but what happened in the meantime? Well, in the meantime, we just see part of the phosphorus that we expect to see. And in particular, people that work with observation estimated that phosphorus is depleted by a couple of orders of magnitude. When present, is found in the form of phosphorus monoxide again, or phosphorus nitride, but is only seen in area where high energy area, where also things that are not normally volatile would be in the gas phase. All this information tells us that while phosphorus is continuously present, has to be locked in a certain form on grain. but we don't know what kind of carriers could be responsible for that. So if we want to investigate more what happened to the phosphorus, we have to ask ourselves a few questions. And the first one is what kind of phosphorus carriers are reasonable. And then we have to evaluate how refractory these are, because of course, if they're very volatile, we should be able to see them in the gas phase, which we don't. To determine how refractory something is, we can use binding energy estimation. And then when we found reasonable carriers that have the right characteristic to match the observation that we have, observational data that we have, we can start to think about how could they form on grains and how efficient their formation is depending on the environmental conditions. Starting from the first question, of course, we want to look at phosphorus oxygen containing molecule. And that's because all the observations tell us that PO seems to be the most abundant feature. Then we want to have molecules that are a little larger than the simple phosphorus monoxide, because the larger a molecule is, the more likely it is to be refractory. And then we need to find a plausible grain formation network. On this, the simplest possible reaction pathway is atomic addition. Atomic addition are generally just limited by the diffusion of the atom. In our case, we choose to use oxygen and hydrogen. And so they are generally barrierless. And we can imagine a phosphorus monoxide molecule forming in the gas phase, then slowly freeze out onto the grain, and then react with oxygen or hydrogen to form PO2 or HPO, so more complex phosphorus-containing molecules. And of course, this very small network can be expanded to form more complex molecules. We choose to stop at HPO3 and H2PO just to test out our model, but this could virtually keep going to bigger molecules. So now we have a few carriers that we think could be reasonable to deplete phosphorus on the grain phase, but we don't know how volatile they are. So the next step, as I mentioned before, is to determine the binding energy, and you can use several different methods to do so, and the laboratory experiment will definitely be the most accurate. But in some cases, like ours, is basically impossible to run an experiment. So what we decided to do is to use computational methods, and in particular, electronic structure method, to estimate this binding energy. One important aspect of this is to determine how the ice surface looks like. And we choose to use a very simple system of 2 water molecules to mimic the ice surface. Then we run 3 calculations. We calculated the energy of the ice surface by itself, the energy of the molecule, and the energy of all 3 molecules together. The difference between the first 2 energies and the last one gives us the binding energy of the molecule. So how much we need to give to the system to have the molecule of interest detached from the surface. Of course, we run this calculation for several different molecules, not only the phosphorus molecules that we're interested about, because we wanted to benchmark our method. And what we found is that all the phosphorus oxide molecules are more refractory than water. And this means that they are quite refractory. And if we extend this into a disk system, means that we should not expect to see this molecule in the gas phase, but rather we should expect them to be in the ice, on the grains, well past the water snow line. We have now our selection of molecules, and we know how refractory they are. So the last step, the last question for which we need an answer, or at least an intuition, is how well they form on grains. And to do so, we choose to use UCL Chem, gas and chemical code that was recently developed by John Oldship. And we use this code in combination with a reaction network that include many reactions that are not phosphorus-based, as well as a base phosphorus reaction network that was published in the literature in 2018. This base phosphorus reaction network include already gas phase reaction and grain phase reactions, but it did not include molecules as H2PO, PO2, or PO3. So it stopped at HPO. This means that we were able to add our oxygenation and hydrogenation reaction to the system and test how they affected the chemistry of phosphorus during evolution. So here again is our mu network, and I want to tell you a couple more things about this. In particular, the only way that we have to effectively enter this reaction network is through PO. So PO forms independently in the gas phase through reaction that have been known for a while. And then as the cloud collapses, it will freeze on the grain and then enter our system. From there, it can go through hydrogenation or oxygenation, and it can end up in two reservoirs of phosphorus. One is H2PO and one is HPO3. These molecules are also markers because H2PO cannot form unless hydrogenation took place, and HPO3 cannot form unless oxygenation took place. So we're going to use these two species as marker for the chemistry that take place. Another important aspect is that lately, people that model phosphorus chemistry use initial abundance of phosphorus that is depleted by a couple of orders of magnitude. And this is to match what the observation tells us. But since we want to know how much phosphorus we can actually store into these carriers, we started from non-depleted phosphorus abundance. Concerning the cloud, we started from a diffuse cloud scenario and then slowly increased the density until a dense cloud scenario was reached. In a condition like this, we will expect the temperature to decrease from about 80 Kelvin to about 10 Kelvin. But the software doesn't have this capability at the moment. We're working on implementing it, but it's not something that it was ready to be used. So instead of waiting, what we did is to take 3 different temperatures, trying to pinpoint different behavior that could occur at different temperature, basically to see if temperature was an important parameter for our chemistry. Starting from the 10 Kelvin scenario, you can see here 3 plots, and at the bottom is just phase distribution, so how much gas versus solid phosphorus we have as the time goes by. And of course, as the time goes by, we have that the density increase. And then we have the red line is the fraction of phosphorus oxide, including PO, over the total phosphorus that we have. And on top, we have the fraction of phosphorus oxide that is converted to higher homologs. So what we can see here is that as the bulk fraction increases, so as the freeze out starts, the surface chemistry becomes important. And so we have that the phosphorus monoxide that froze now is converted to higher homolog phosphorus oxide. But unfortunately, if we look at the plot below, we see that only 1% of the initial phosphorus is actually converted to bigger and higher homolog phosphorus oxide. This is probably due to the fact that at this temperature, only hydrogenation is available for these molecules, because the diffusion of oxygen is not as efficient at such low temperature. In any case, a dense cloud scenario doesn't seem to be the best scenario for this chemistry to occur. If we move to 20 Kelvin, we still see that we have about 1% of conversion of the initial phosphorus. But now we see that the fraction of phosphorus oxide starts to increase. It seems that it becomes more efficient, especially by the end of the collapse. And if we look at the reactions there, what we see is that at 20 Kelvin, now we have that the oxygenation is viable. The channel is activated, and so we have that most of this phosphorus doesn't go to H2PO, but instead forms HPO3. Building up on that and going to 40 Kelvin, we see something that is finally a good news. So the fraction of phosphorus oxide that is converted to a bigger molecule is about the same as at 20 Kelvin. But now instead of having 1% conversion, we have about 5% of conversion of the initial phosphorus abundance. This, of course, is still not enough, but it's a beginning. It tells us that high temperature can help these processes. And what happened here is that at 40 Kelvin, hydrogenation is almost not present, and then the oxygenation becomes the dominant channel of reactions. And the conclusion that we can draw from this is that in a more diffuse cloud scenario, we have that this grain phosphorus chemistry is favored, which moves us back from the dense to the diffuse cloud. Of course, we still have some problems, and we can look at this. We can see this problem better by looking at this pie chart, which shows for each of the temperature condition the most abundant phosphorus species that we have. And at 40 Kelvin, which is so far the most promising scenario, we see that we are actually working with only about 40% of the initial phosphorus, because 60% of it doesn't react at all. It stays in its atomic form in the gas phase. So, of course, a static temperature scenario, static temperature simulation doesn't work. We need to implement this cool down system. But also we see that in all three cases, the phosphorus nitrogen chemistry is way more effective than the phosphorus oxygen chemistry. And for this, we will need to look more closely to the network that we have and try to understand the relationship between these two kind of chemistries. So this is very much a work in progress. We are just starting to understand how this carrier can form and how much of this carrier we can form in a cloud simulation, but we can still draw a couple of conclusions. First of all, we know that molecules such as HPOY can be very refractory. So that means that if these species form, they could be very good candidates for refractory phosphorus sinks. Also, this temperature exercise told us that a diffuse cloud scenario seems to be where this molecule could form in the highest higher abundance, the most favorite condition for them to form. But we are still working on building a simulation that is more realistic, and for that we're working on creating a cool down models within UCL, the UCL Chem software, and we will also look at the network more closely, because the availability of phosphorus oxide is what determines how many bigger oxides we can form, and the availability of phosphorus oxide is very closely tied with the reaction to form phosphorus nitride. So I hope I will update you soon with some more information, but for now this is it, and I can take any question. Thank you.
All right, thank you, Elettra, for that nice talk. We do have a question in the Q&A tab. So for the rest of you, if you have questions, please do feel free to open up that Q&A tab and type them in there. And if push comes to shove and you can't get the Q&A session working, you can type your question into the chat as well. We'll be monitoring both. So first up, we have a question from Philemon Muhangi, who wants to be reminded which software program was used for the computational analysis.
So for the binding energy determination, we use Gaussian 16. And for the simulation of the cloud collapse, we use UCL Chem, which is an open source software that was published a few years ago by John Holship, and it can be found on GitHub.
Okay. We have a question in the chat from Heather Abbott-Lyon, who asks what lab measurements, if any, would be most helpful to support the computational model that you used?
I would be curious to see if the binding energy that I estimate for these phosphorus molecules are actually correct, because we see that for molecules for which we have experimental values, we are quite close, but I don't know if these phosphorus molecules are realistic. So it would be nice to see how well my computation are compared to experiments. But I will be mostly curious to know what kind of to have laboratory information to then be able to look for this molecule through observation. So it would be nice to see it soon.
All right. We have another question from Vincent Esposito, who asks, have there been mechanistic studies such as molecular dynamics looking at these reactions on the dust grain surface?
As far as I know, in the sense someone studied the binding energies in different ways, but not actual reaction. Nobody studied the reaction, the hydrogenation and the oxygenation reaction. If you have any reference, please send it my way, but I haven't found anything.
All right. I wanted to ask, so when you were describing your calculation of the binding energies, you used two water molecules to kind of represent the surface of the ice, and then you added another molecule. Did you did that calculation at like many different geometries and then kind of calculated an average binding energy? Is that right?
Well, not really. So for some molecules, I calculated more than one. I started from more than one initial geometry, and I found different binding energy, but I always choose one kind of binding energy. So with the hydrogen from the water binding to the molecule. So I just choose that, but of course that's representative only of one specific geometry, is not representative of the distribution of the binding energy that we could have, and also using a small cluster for the water does not tell us anything about long range interaction that could change that distribution. So is a very simple and easy to implement sort of calculation, which was not meant to have precise information, but rather have a general idea where this species sits in the binding energy ladder.
Yeah, that was going to be my next question. Like if you increase the size of the water clusters, is there any like systematic trend if you've benchmarked that with a small system?
So we tried up to 3 water molecules, but there have been studied up to 6 water molecules. And for us, 3 water molecules didn't actually improve much over 2 water molecules. That's why we choose the less expensive system. Other studies saw that up to 4 up to a tetrameric cluster, there is some improvement, but not much after that. So it seems that for like a one binding energy estimation, a single value of binding energy in a small cluster system between 2 and 4 seems to be the best.
And my last question for you was, like you talked a lot about the competition between PN and PO at the very end. I wasn't looking for it when you showed your initial table or your chart of binding energies, but how refractory is PN compared to PO?
So is a little more volatile. So PN sits about here. I don't know if you can see my cursor. PO sits here. So yes, we should be able to see a fraction of PN more than PO because of the difference in volatility. But I haven't looked closely of the relative abundance yet to know if that could be the only factor. But what we see in the cloud simulation is that PO and PN have overlapping chemistry. So there are some reaction that consumes one of the other. And so depending on the scenario, on the environmental condition, you can have that the abundance of one prevails on the other. Of course, it's a model, so it's not complete, and it could be something that we introduce as we run the simulation, but that doesn't reflect reality completely.
All right. Well, thank you again, Elettra, for that very nice talk. We are going to move to our second speaker for today, and I'm happy to introduce Dr. Uma Gorti. Dr. Gorti hails initially from India, where she received a master's degree from the Indian Institute of Technology in Bombay, and then a PhD from the Indian Institute of Astrophysics in Bangalore. After completing her PhD, she came over here to the US and did a postdoc with David Hollenbach at NASA Ames. And she has been working at NASA Ames since, and for the past 10 years has also been working at SETI, where she's currently the chair of the Department of Astronomy and Astrophysics. So her earlier work has been on the interstellar medium and star formation, and more recently, she has been working on the formation and evolution of protoplanetary disks, which is, I believe, what she's going to be telling us about today. So with that, welcome, Uma, and I'll hand things over to you.
Thank you very much. Thank you for the invitation to speak here. And I just wanted to say that I guess I will be telling someone to forward my slides since I'm not in control. I guess. Correct?
You may be able to request remote control under the view options menu if Chris allows you to
Okay.
do that, and then you may be able to click through. I've never tried that before, so we'll see if it works.
Yeah, neither have I. Well, okay, so I'm just going to, yeah, so this is going to be a talk on physical and chemical models of protoplanetary disks. So these are disks that form planetary systems. And over here, I sort of have this, just to establish context, what we're talking about. So if you start at the very top, you can see that you have a dark cloud. I've obviously ignored everything that goes on in the interstellar medium that Elettra was talking about. There's already a lot of complexity there. But we start here with the dark cloud, and that undergoes collapse. So that's the next, set of figures where you can see that this dark cloud then forms a protostar at the center. And because this cloud is spinning, it then forms a disk, and there's also a jet associated with accretion onto the material, onto the central star. And these disks initially are sort of quite massive. You can see that in the spiralums, at the figure on the top right. And eventually, at some point, they form planets, and the disk evolves. You can sort of get to these more symmetrical structures, and then you form planetary systems. So that's sort of this planetary system around the star HR 8799 that you can see. And this is also the process by which we think we form our own planetary system. And along with the planets, you also form asteroids, comets, IDPs, which we know organics are present in large amounts and that have been detected. And ultimately, we're sort of trying to see, well, what of this is relevant to the origin of life, right? So this is sort of the broad context in which the talk is placed, but I'm going to be talking mostly about the disks themselves and the chemistry that goes on. Next slide, please. So this is a nice schematic from an old review by Henning and Semenov. And this sort of shows you, what the disk environment looks like. So you have a central star, obviously, and you have a disk that's sort of accreting on, and then material accretes onto the central star and then produces UV and X-ray radiation. So on the left-hand side, you have the dust component, so which is sort of, present in the interstellar medium at some 1% mass level, and the disk obviously inherits this interstellar medium material. And some of the pertinent questions here are all these evolutionary processes that take place. The dust grains do grow and eventually turn into planets. So how does that happen? And what role do winds play? This is not in the original review. Sort of added these yellow arrows to indicate that the thermal and magnetic winds that go on. And how does material get transported in the disk? What causes turbulence? The grains then settle, and then there is a snow line. You actually have planet formation happening at some point. We don't know when or how. And all of this takes place. And this also because these dust grains are solid particles, they drift in the disk relative to the gas, and they sort of get accreted in. And there's a lot of dynamics that goes on. And all of this is pertinent to the star formation process, so to the planet formation process. And on the right-hand side, you have the gas, which is sort of, you can see that there is the UV and X-ray photons that come from the stars sort of illuminate the surface layer. So that's a red region where you can have radicals and ions. A little bit more in the shielded interior, you begin to have molecular chemistry, and all the way the midplane, close to the middle, you could be so cold enough that you could have ices. So then again, what sort of processes happen and how this happens depends on the disk conditions, like for example, the density, the gas temperatures, the dust temperatures, the level of ionization in the disk, and of course the chemical processes, many of which are unknown. And to top everything, while all of this is happening, the disk is actually evolving because the disk's lifetimes are only a few million years, and the disk disperse right about the phase a bit right after planet formation. So the disk is rapidly losing mass at all this times, which again changes the thermodynamic or dynamical conditions in the disk, like the density structure and even the levels to which ionization can penetrate, which then obviously impacts the chemistry as well. Next slide, please. So in most of this talk, I will be basically describing models. So this is sort of more a modeling based talk, just to sort of understand what sort of input we can give, what kind of mathematical models we can construct from the physics and chemistry that we think we know, and then try and reproduce replicas of these disks we can compare with observations, and then try to infer what sort of processes go on and how disks evolve and how planets form. So at the very basic level, we've got these three inputs, so which is essentially the stellar mass. We need to know that, and we have some idea of what sort of photons come out from the star, from the X-rays and the UV. We have some measure of this. We can actually measure this. And then one of the next ingredient is the disk mass, which we don't know, but so this is a key input parameter. So we need to know how much mass is in gas and how much is in solids. So while in the interstellar medium, we know that there's 1% solids because of the fact that some of these solids are forming planetesimals and some of the gas is being removed from the disk by winds, this does not necessarily have to stay constant. And this is in fact something very interesting for planet formation and disk evolution in general, how the mass of the gas in the disk sort of varies with time. So this is something we can specify. So this is an input into these physical chemical models. And then we have basic physics, which is just basically your Newton's law. So we have to, sort of have this disk, which has to be in some sort of force balance if there's not major motion going on. And so radially, the grains are sort of moving in Keplerian orbits, and then the gas is slightly sub-Keplerian because it also has a radial pressure gradient balancing it. And vertically, again, you have a pressure gradient that balances gravity. So to do this, you obviously need to know the pressure, which means then you need to know the thermodynamical state of the system, which means you need to know the temperature and the density. Next slide, please. And so we can sort of put this together. So this is sort of the basic way you construct a disk model. You start with this top slide, which is the top box, which is just the surface density, which you have prescribed. It's an input. And whatever density distribution you have, in the end, when you integrate, has to sort of give you back the mass that you put into this. So that's sort of a constraint on what the density distribution vertically is. You also have the next equation, which is just basically the gradient of pressure, which is balancing gravity. So this is just essentially Newton's law in a fluid form. But then again, here, there's a slight complication in that you also need to know the pressure. The pressure is, again, a function of the density and the temperature. There's also mu, which is there's a gradient, but let's ignore that for now. So that, you can just think of pressure as just being a product of the density and the temperature. So if you know what the density structure in the disk is and the temperature structure in the disk is, they basically have to satisfy these constraints in that if you compute the pressure, then you have to get this pressure gradient, and then you have to recover the surface density that you actually gave in. And how do you do this? You start with some guess value, and then you try to compute what the heating and cooling is in the disk. Then you have to figure out, what photons escape because the disk is quite optically thick in most of the disk interior, and so all the photons do not escape. So you have to solve for the photons that escape. Solve for the chemistry because then line cooling is one of the dominant coolants. So all the emission, that energy that's being lost from the disk is being lost via. Sorry about that. Is being lost from line emission from trace species. And the dust, as we already alluded to before, and I showed in the previous slide, is also colliding, and this sort of provides opacity as well. And so what you have to do is sort of solve these things iteratively. So, and the idea is to iterate over this many different times. So you have these constraints, and then you end up finally with what I've circled over here, which is you're sort of looking for a density distribution, gas and dust temperature distribution, which can also be a function of the grain size. And what I've denoted by X is basically the chemical abundances in the disk. Next slide, please. And so the surface of a disk is something that's dominated by the fact that you have photoreactions. So this is, it's basically just a combination of PDRs and XDRs. And shown here is a sample X-ray spectrum and a UV spectrum from stars. So basically, because of the accretion onto the central object, and because of the fact that there's the interiors of low mass stars are convective, you do have a lot of X-rays as well. And then what you need to do is, and of course, all your species have some cross sections that you can fold in with this X-ray and UV spectrum. And the only difference between the standard PDR and XDR models from the ISM is essentially that is sort of illustrated in this little sketch I have in the top right. You have a star, and the only thing that really changes is the geometry, right? So you have oblique incidence, and then of the UV photons, and then you have the escaping radiation that goes vertically up or down. So basically, this is inherently a 2D problem rather than the 1D problem. And some other small minor differences are that the dust grains are growing, so the FeB opacity is lower, which means that gas shielding could become important, and you sort of need to solve for this, these cross sections, which I've shown here, for example, the water cross section from the SWORI database. And you need to solve this as a function of local conditions because it depends on how much of the absorbing species there is. And so this sort of complicates things a little bit, but this is still essentially very doable and things that we know how to do. So basically they're just sort of tacking on a PDR and XDR model at the surface of the disk. The next slide, please. And so this is sort of, things that you normally have. You have a bunch of heating processes. I've just sort of listed a few of them here. You could have cooling. And because you're doing this heating and cooling, you need to sort of then fold in a radiative transfer model, which sort of then describes how radiation is escaping the disk. And then you also have the chemistry. So right now in our models, we have a lot of species and many thousand reactions. And a recent addition, so these are models that I've built over the years with Dave Hollenbach, starting way back in early 2000, I think. And so now recently we've added three-phase grain surface chemistry. So this is a recent addition. So we were sort of only concerned with the surface before. And now we're sort of looking at the interior of the disk. Next slide, please. So this is something that work that's been done by Maxime Rowe, who I've shown here. He joined NASA as a postdoctoral fellow a few years ago. And so this is sort of largely his work. So he did this, he has this very elaborate three-phase grain surface chemistry that he built for the ISM, which he then transported over to OAT disks. And so this is important because, as you'll see later, the interior regions of disks are dominated by the grain surface chemistry. And in reality, you just have two layers. You have the PDR, XDR on top, and then you have this interior region where it's all grain surface chemistry. And you have the usual slew of reactions that can happen here. You can have accretion of molecules. And this is also, again, mediated by the surface area that you have, which is modified by the growth of grains in the disk and the fact that ices could be stickier. You can have desorption, photoprocessing of ices, and you could also have a variety of reactions facilitated by the fact that these molecules are adsorbed onto the surface, and that's sort of shown here. And I'm not going to go into great detail. The next slide. So what you can do, so this is something I wanted to say. I'm a physicist by training, and I mostly work in physics, but this is an AstroCheminar talk, and so I decided that I'm going to focus on molecules, which sort of are the chemistry according to Eddington, where I really like this quote here. So I'm going to focus mostly on the midplane region and focus on the molecular parts of these disk modeling studies, and not on the surface layers, which is also usually actually work I have worked on much more. The next slide, please. So here is a result from some of these disk structure models, right? So I've got two sets of models here. So the top set of models, it's a very confusing plot, but I will sort of walk you through what I would like to emphasize on. So the top set of 8 plots is one disk, and the bottom set is another disk, and they differ in their mass by around 10. So this is the top disk is a massive disk, the bottom one is a lower mass disk. And now I'd like to draw your attention to the black lines. So if you look at the line that's marked AV of log AV of 0.0, so that sort of roughly demarcates the region above which you have stellar photons impacting the disk, and below which they're sort of roughly attenuated. So that's the optical depth in the visual. And you can see that in the upper part. So sort of if you look at everything, what I'm going to call the surface, which is the region above this AV of 1 layer, the disk structure looks roughly the same for both the disks, although you have changed the mass of a disk by a factor of 10, right? So if you look at the density, which is the first plot here, in the top row, the first plot, and then the top row of the second set of plots, because the density structure looks roughly the same. If you move over now to the temperature structure, which is the second plot, the second column, well, this is going to get confusing because I don't have a cursor. But yeah, so basically, if you look at the second, yes, that one, exactly, thank you. So if you look at that, you can see, and you look at the corresponding plot below, you can see that the temperature is also roughly the constant. This is the gas temperature. The dust temperature is a constant as well. And because your density is roughly the same, you also have a similar UV field, which is the last panel here on the left, which is the log of G0. And you can see that they look the same in both the panels, right? And if you go to the second row for each of these sets, you can the first panel I have there is the cross section, which is relevant for brain surface reactions, for example, or how much absorption takes place. They look a little different, but if you look at the cross section per H, which is what's relevant for most of your chemical reactions, they again look very similar. So the only things that seem to differ a little bit are the cosmic ray ionization at the surface, and to a very small extent, the X-rays. But so at the surface of the disk, nothing is really changing, although you've changed the mass by more than an order of magnitude. But if you look at the midplane, you'll find that, again, there is a small difference, but the density is clearly very different from the top disk and the bottom disk. So if I'm calling your attention to the region marked below the 0 layer, the 0.0 black line, you can see the density is much lower. The temperature is sort of roughly the same, not too different. And then the UV field, of course, is slightly different, right? So if you look there, you can see that there's more UV penetration for the low mass disk. And how did that happen? Yeah, so that's, so you have more UV in the higher mass disk, and that's just because the disk is flared, which I'm sort of not getting into in great detail. But you can see that there is more UV for the lower mass disk. The X-rays, not very important here. And then again, the cosmic ray ionization rate is again is higher for the low mass disk. So apart from these two things, which is basically the density, the UV field, and the cosmic ray ionization rate, even the midplane looks roughly the same. But these are sort of the main things that are changing in the midplane. And so go to the next slide, please. So you can now look at where the common molecular gas phase species are and where their emitting layers are. So this is a plot. Again, it's the same sort of plot, radius along the x-axis and a sort of scale height z over r on the vertical axis. And you can see again here that most of the abundances dominate in two main layers. So one of them is right near the H2 and CO photodissociation front, which is right at the top. And this is sort of obvious because this is where you have photons dissociating. You have a lot of, for example, radicals, and you have C+ and things like this to sort of initiate reactions. And you can see that that is a region where you have some emission. A second interesting region is right near these two lines that are marked as 0.0 and 1, so which are basically AV of 1 and AV of 10. And you can see that there is sort of a second layer of emission in there. And this is near the water slow line. And what you're looking at for many of these species is basically desorption of these species into the gas phase. And the midplane is mostly non-emissive, right? So all your emission is sort of bounded by either you have emission at the surface, and this is, this is not true obviously for every molecular species, but this is true for species that are commonly observed, which is sort of what I have put here. Some of them, like methane, for example, have not been observed but I've just sort of put it there because it's one of the dominant species. And you can see that most of the emission is dominated by one of these two layers. The next slide. And so this is now the midplane. So all the S's denote the solid phase. And here now, so these are all species that are on ices. And you can see that, again, there's a very sort of basic separation or demarcation in that if you look outside of the region where the dust temperature falls below about 15 Kelvin, so you only have hydrogen that moves on grains, and you have basically hydrogenation ruling the chemistry. In the inner region, so which is roughly inward of about 100 AU on these plots, there is more, the disk is warmer, and now you can even have mobility of radicals and you form more complex molecules. So that's sort of roughly the structure of the disk, right? So you have this region on top, which is dominated by those photons in photodissociation. And then in the midplane, you have these two sort of regions, an outer disk where you have hydrogenation and inner disk where you could have more complex chemistry. And of course, you still need to form radicals in the inner surface of the disk, which is, in the inner parts of the disk, which is quite shielded. So here now the cosmic ray ionization plays a role. So this is sort of where disks start to slightly differ in how they are structured. And this, I should point out, is not something that is very well known, but it does seem to dictate whether you can form, the ability to which you can form complex radicals in the inner part of the disk. The next slide, please. And so what can you do with models like this? So that was sort of just the, an overview of the kinds of results you can do. So we can look at, for example, observables. So this is a paper that we recently wrote where we looked at the emission of the CO isotope as a disk mass tracer. And we conducted a very limited survey where we vary the gas and dust masses, and then you compute the chemistry and you can compute the C18 emission. And what you can see here, the top row is the, I'm going in order, is the density, the gas temperature, dust temperature, and the cross section. In the second row, you have number densities of various species, and you can see that, for example, the CO and its isotopes are frozen out in the, below the AV of one layer and are only present at the surface, right? And then you can compute the emission using range of transfer tools, and you can sort of see, well, how does emission compare with what you observe? Next slide, please. So what we found here, and this has been found before, it's not that, but what we found is that the fact that the CO is not frozen at its snow line, but actually frozen where CO2 freezes out, and you can see that in this little slide here, the little plot here on the top right, which shows that water condensation front, so which is in red at a given height in the disk. So on the horizontal axis you have the height, and the vertical axis you have the abundances, and so that's sort of roughly where water freezes out. If you assume that CO is just freezing out by itself, then you'd expect that the CO would freeze out in this region where the blue line has sort of dropped down and the dashed line picks up, which is the CO abundance in the gas and solid phases. So if you do a simple balance between accretion and desorption, this is what you'd find. But if, on the other hand, you allow for reactions to happen at the surface of the grains, so in this case, you have ice on grains being exposed to UV, which then gets dissociated into OH and H. And any CO that sort of happens to freeze in this region then sort of forms CO2 very rapidly. So the whole, in this layer, you have a conversion from CO to CO2 quite rapidly. And you can see then that what that means is that you have the CO snow line, then you have an intermediate region with CO2, and the gas phase CO actually moves further up. So what this means is that since you move the snow line vertically up, you actually have less emission of CO. CO line is not as bright. And it means you basically get, for the same mass in the disk, you get less emission. So the next slide. What we found is this shown here is a plot of the CO luminosity versus the mass in the disk, and the dotted lines are connected. The dots connected are the model results, and the black lines are a recent ALMA survey. And what we found is that you can sort of pretty much recover what you see with no additional depletion, which has been found by many other authors. And I should actually at this point say that this result is sort of goes against the current trend, which is that many disk modelers find that they need a depletion of both of C and O to explain the C18 results. And what we found, which is kind of contrary to what people found, is that we don't really need to deplete CO at all. And you just freeze it out in your account for this extra formation of CO2, and you can sort of pretty much recover the results. Next slide, please. And there is an additional sort of glitch in the whole thing, is that basically you have very bright C2H emission from disks. So these are work by Miatello et al., which shows emission from C2H, and they found that C2H is way brighter than you'd expect. So which sort of indicates that the high volatile C/O ratios. This is something we also found, and we find that if you see that if you change the C/O ratio, so this is one disk and several observed lines on the bottom. And the observed lines are, the observed points are marked in these black dots, and you have various models that are indicated in various colors. And what you can see is that if you want to reproduce, for example, the C3H and the C2H emission, you need something like a depletion or a change in the C/O ratio between about 1 and 2. And that's sort of indicated by the fact that you have excess hydrocarbon emission at the surface. Next slide. So this is So this is something that was being found even by groups that sort of require a dynamical depletion, to explain the C/O ratio, and they find that you can't sort of really explain the fact that the C/O ratio is is higher than what you see. So this then leads to the big question of whether you have any cycling between the carbon grains and from the dust, which is in the form of carbon, into the gas phase. And this is something I've recently been interested in because it just sort of is super interesting that you could have the cycling of carbon from into the gas phase. Next slide. So this is recent work we've done at Ames. So Lisette Gavilan, who works at Ames, did this experiment where she used grains that were synthesized in the lab using the COSMIC facility at Ames, and then exposed them to synchrotron radiations, and see how much you could destroy carbon dust by X-ray radiation, for instance. And shown here in this plot, for example, the blue curve is the absorbance before exposure, and then you can see that after you expose with X-rays for about 11 hours, you find that most of the carbon dust has been destroyed. And this is because you sort of create these major structural changes which can destroy the carbon grains. And we sort of applied this to disks, and we did find that there was some destruction. The next slide, but the next slide, please. Yeah, but we just need more efficient destruction, and I should be sort of doing new experiments, a plan to sort of look at this in more greater detail to see if there's any sort of chemical destruction of carbon dust. And I should point out that this has been looked at in the past, and not, I've listed several authors here, and this is going back to the 1990s perhaps, but there have been no efficient destruction mechanisms found yet, although there is evidence from, so let's say, the solar system observations that there is a carbon gradient in the disk and that there is some destruction of refractory carbon. So this is ongoing work. The next slide. We've also been looking with Scott Sanford and at NASA Ames, and quantum chemist Tim Lee and Partha Bera. We've been looking to explore to what extent we can have abiotic chemical complexity proceed in disks. So, for example, we have so we know that from experiments that if you irradiate astrophysical ices, you can produce these organic residues, and so this is sort of shown in the experiment that's on the right-hand side. And so we're sort of trying to conduct new experiments where we use ice compositions as we get from the models. So that's on the left. So you can see that if you're looking at the inner disk, then you have a much more complex distribution of complex organics, whereas ices are more simple and basically just hydrogenated ices in the outer part of the disk. And we're sort of trying to do these experiments to see, whether you could produce these organics. And of course, you need UV because that's how they form in the lab. So it's not enough to just have the ices, you also need to expose them to UV radiation. Next slide, please. And this can happen if you have ice-coated grains that get transported vertically up. And so this is a plot from Chesler and Stanford, and you can see that there's a height versus radius, and all these white squiggles are basically a dust grain dynamical motion going up and down. And you can see that as the grain moves, it can sort of go into these regions of the surface where it can get exposed and come back down. And they calculate that the incident photon flux can be quite high. So we're sort of trying to do this in a full multi-fluid simulation, and I'm going to show, it includes transport simulations. We're sort of looking at dust and how chemistry occurs in dust as it moves through the disk. Next slide, please. So these are some preliminary results where we tried to look at a single grain, so sort of along the spirit of what has been done earlier, to sort of see what kind of chemistry is important. So we have a bunch of processes which we include, which is gas drag, settling of grains because of drag again, turbulence, diffusion of dust, and a whole bunch of collisional processes. But we're just following a single grain. We draw all the background conditions from the disk simulations, and sort of in a very simple scenario, what we're assuming is that if the grain grows and if it collides, it grows and acquires the ices of the collider. And if it fragments, then we redistribute the ice according to the mass. And of course, if any of these grains then get exposed to UV, and if you have the right sort of ices present on the grain, then you can form a residue on it. And the next slide. So this is sort of the first slide here shows the the excursion of a grain and layers where you can expose to UV, which is the yellow band on top. And if you do that, the bottom then shows these orange spikes, which are basically how much residue you produce if you had that much water ice with the it's basically a function of water ice. And also in this case, we produce residue mostly from methanol. And shown here is, the kind of, is the mass that you can convert into ices. And you can also see that this actually changes as a function of radius, and it's more efficient in the outer disk. And so which probably means, significant transport if you were going to form these kinds of meteoritic and cometary residues, and you need to bring them in from the outer regions of a solar nebula. So the problem with this model is that really that it's just a single grain model, and it's kind of not fair to treat the grain in isolation because the whole background is also evolving. And so we're sort of doing this ongoing work where we're trying to treat the whole thing as a fluid and construct these sort of chemodynamical simulations to see where you could form organic residue disks. Next slide. And so that's my final slide. So the takeaways are just that protoplanetary disks are complex. And so they're very interesting systems in that they have the physics and the chemistry and the evolution is all very tightly coupled, and each impacts the other. As the chemistry is sort of crucial to inferring the disk conditions and understanding how disks evolve and planets form. And also the emission lines arise mostly from the surface, so you really need to know the structure of the disk. And so one result that we find is that we can in fact use CO isotope emission lines to measure disk mass, and ongoing work that sort of suggests that you could form prebiotics in disks under certain conditions, and that exploring how carbon could be cycling between the gas and solid phases could be something that could be very interesting. So next slide. And thank you very much for your attention.
All right, thank you, Dr. Gorti. We do have some questions that have come in. I'll start with one of those. So do your models look at all at how the composition of, say, an ice surface on a grain may affect the desorption rates of the compounds that are, say, inside the ice? Like if you have a more hydrophilic versus hydrophobic composition, does that affect like desorption rates?
Yeah, so actually so we assume that the ices are mixed because that's the simplest thing to do. And so most of it is water ice, really. And I did look once into whether, if you had, for example, a PAR grain or a carbon-coated grain, which could be more hydrophobic, whether that would impact the rate at which you could form ices. But then it turns out that you just need to form that first layer of ice. And with the densities in disks, this is really not that big of a difference, because once you form the first layer of water ice, which is the predominant component of the ice, you could have any substrate and things just proceed in a similar way. So it turns out that it's not very important, but this is not something we've done, we've sort of accounted for. And I must also say here that many of these binding energies, rates, reaction rates, etc., are unknown. So we try to put in the few that we do know, but there are really scores of them that you don't.
Yeah, that was related to one of the questions I had written down during your talk, which is like when you're modeling this prebiotic chemistry that may be taking place on ice surfaces, especially like accounting for, the possibility that a grain could migrate up to the top layer, become irradiated, and fall back down. Like how uncertain are the chemical networks that you're using to produce these?
So producing that chemical network is actually the goal of of what we're trying to do. So that was the synergy between the lab and the quantum computations and the models, right? Because most of the time you're not actually going to see any of these really complex things. You're at the most going to see probably desorption products or something. So there's not too much you can do to sort of benchmark the models. But what they're doing, so in the lab, we can sort of determine, well, if you have these compositions, these are the classes of molecules you can form. And then, sort of relying on the quantum chemical folks to sort of give us some sort of a reaction rate, because that's kind of how we model everything. We sort of just put in a reaction rate. For the residue that I showed, what we used was we used ices. And then we sort of used a fraction of, based on just a few points that we had in the observation. So what we said was, okay, if you had methanol and which you irradiate, if you photodissociate because you see photons, there's a certain fraction that gets converted to residue, and that fraction is what we've taken in. So now we assume that the residue actually sticks on the grain and does not leave because it's just very tightly bound. And so these are the sort of things, this is all very exploratory to a large extent.
Yeah, so one as you were just discussing, like we can have like laboratory inputs that help constrain parameters in the models. We can have theoretical inputs that help constrain the models, but the models, of course, are also very useful for trying to help interpret astronomical observations. So my question for you is, like, if you had control of ALMA for, a whole week, if you could control that instrument, what observations would you want to make with that telescope to best, constrain something important about your disk simulation model?
Yeah, right. So there's actually, this is a good question, because something we've been doing in parallel, which is there is actually a ton of ARBO observations already in the archive, right? But I think that so to do what we want to do, which is the sort of models we're constructing, what we really need to do is take something like the recent map survey that that came out from the lab survey from ALMA, and I think you had a talk on that sometime earlier. So you sort of need to have one disk, and because you do need to sort of at least pinpoint the as much of it that you can constrain. So like, for example, you have the UV field, the X-ray field, all of this can be measured. And if you know the mass of the star and you have other inputs, so you want to sort of pick one disk and collect all the observations that you can for that disk, and then try to put together a model. So there are currently several puzzles already. One is, for example, the excess hydrocarbons that you see. And so there is also, in our models, we produce less HC3N compared to what you observe. And so these are all things that I think are indicative of some sort of grain surface chemistry that we still haven't understood, or we do not have in our models. And maybe they are the product, because that's what you can see. So if you really have these very large molecules, at the most, you're going to see some sort of you would desorb them, or you would desorb some byproduct, you're going to see smaller molecules, which hopefully is something that you see at these surfaces. So this is, it's actually quite involved modeling, and it takes considerable effort to do this, but it's something that we are sort of looking into. And I don't think I would need new observations, frankly. I think there's plenty out there already.
All right. Well, we're at the top of the hour, so it's about time for us to wrap things up for today. So thank you to Dr. Gorti and to Dr. Piacentino, and also thank you to all of you who are here in the audience today. So if you would like to give a contributed talk at an upcoming AstroCheminar, please do go to our website. We have a form there where you can submit an abstract, and we think this is a great opportunity for students and postdocs, especially, to get their work out in front of the community. And we plan to be back with you next month for another AstroCheminar. Keep an eye out on your email on the mailing list for information about when that's going to be. In the meantime, if you want more astrochemistry content, you can check out our YouTube channel, where we have many of our past AstroCheminar events. You can also check out the website of the astrochemistry discussion site at discussions.astrochemistry.net. They are off for this month, so their next seminar is intended to be toward the end of November, but they have a video archive, as well as some new short videos on the JWST that are worth checking out. So we will see you next time. Thanks again for your attendance, and enjoy the rest of your day.
Okay.